Hi, my name is Julia Silge, and I'm a data scientist and software engineer at RStudio. And today, in this screencast, we are going to use this week's Tidy Tuesday dataset on Mario Kart world records. And we're going to train a model to predict whether any given world record was achieved using a shortcut or not. So we're going to use a decision tree model for this, and decision tree models are so nice. You can understand them; they're very explainable, and the pre-processing required for decision tree models is very low maintenance, which is really nice. They can tend to overfit, if like when we do a single decision tree model. So we'll be sure to tune them carefully on resampled data so that we do not overfit the decision tree model. We're also going to walk through and talk about how to do a partial dependence profile or a partial dependence plot for the probability of using a shortcut with the time. The length of time like the world record time. We'll use the DALX package for that, which works really well with tidy models. Let's get started.
Okay, let's learn about Mario Kart world records. All right. So let's look at this data. So we have here, this is this week's Tidy Tuesday data. We have information about what date the record was, what the date it was made, the time. This is in a different time period. This is in in seconds. How long it was a record for, the person who did it, whether it used a shortcut or not, whether it was a 3-lap or I believe a 1-lap. Let's look at that. Count type, single lap or 3-lap, and let's see how many tracks there are here. 16, so that's not too many. That's about right, or not about right. That's a reasonable number to include in a model here. And then that shortcut, there we go. No and yes, and there's a little bit of some imbalance there, but not too bad there. All right, so that's the data we have. So what we're going to do here is we're going to train a model to learn and predict whether based on these other characteristics of the record, did someone use a shortcut or not? Like, can we predict that? So let's just make like one exploratory plot, date, time. Let's say color equals track, and then let's put points so we can maybe say like over time and kind of see how that changes. So I don't want to see all those 16 legend, tracks on the legend, but let's put a let's do a grid, and let's put on the rows, let's put that whether it is 3 laps or 1 laps, and on the columns, let's put the shortcut there. Nice. Okay, let's make the scales free like that. Okay, so we've got no shortcut in this column and yes shortcut this way. We've got single laps and 3-lap times here, or like when they were made. Was it during a single lap or a 3-lap run? And no shortcut, yes shortcut, no, yes. Okay, kind of interesting there. And we do see some drifts down, but then it's pretty stable after about 1999 or so. I don't know. It's pretty interesting. Okay, so this is the data, and you can see, these are like different tracks and these different colors, which is also very interesting. So we're going to use all this data, and we're going to try to build a model to tell the difference between a record that was made with a shortcut, taking a shortcut on the track, and one that was not. So let's build a model here. So let's load tidy models here. Let's go like that, and then let's set up our data spending, spending our data budget. So let's look at records again. I think so shortcut is our outcome. Let's use track, type, date, and time. And if it is a character, let's change it to a factor. Factors are generally better for modeling. Let's do stratified sampling. We have a little bit of imbalance, but I think I'm not going to handle that this time. So that's a split, and let's make our training set from the split. Let's make our testing set from the split. And then let's make a set of resamples. So Mario folds, V fold, CV. So we resample the training data, and we can also do stratified resampling there. See how there's a very small number of examples in the assessment set of each resample. So let's change that from vfold cross-validation to bootstrap resamples. I think that will be better. Okay, so we're going to do a pretty straightforward model, but we are going to tune it. So we're going to do a decision tree model. So let's call it tree spec. So we're going to do a decision tree, and we're going to let's tune the cost complexity, and let's tune the tree depth. We could also tune min n if we want. We're going to use the engine rpart, and we are training a classification model like this. So let's clean that up a little bit. Like so. So this is our model specification. So our model, we say what kind of algorithm we're going to use. We're going to tune these, because decision trees overfit pretty badly. So we generally and they generally do need to be tuned to perform well. So let's set up some values for these that we want to try. So let's make a grid, a regular grid here. Let's call it grid regular, and let's say cost complexity, tree depth, and let's say levels equals 7. So we're going to try 7 different levels of each of these. So that means overall we're trying 49 different models. And now let's put those things together in a workflow. So we're going to start by declaring our workflow, and we add our model to it, which is tree spec. One great thing about tree-based models is that they are very low maintenance when it comes to pre-processing. They don't require much. They are what did I do wrong? Set engine, set mode. Whoopsie daisy. Okay, there we go. So the the tree-based models, like a decision tree, are very low maintenance when it comes to pre-processing. So when we look at that training data, you know, we've got a date, we've got a number here, we've got factors, one of which has 16 levels, and that's all totally fine. We can just like throw that all into the decision tree and it will work great. Or hopefully. I mean, it will. If it doesn't work great, it's not because of the pre-processing. So let's use parallel processing to make this go faster, and let's put in our workflow. Let us put in our resamples, which are these bootstrap folds we made. And we are going to have a grid, which is this grid of possible values. And then let's save the predictions in each for each resample, so we can make some plots. Let's call this tree res, like this. Okay, so and then I'm going to start this, and it is going to train. So what it's going to do for those 49 possible decision tree models, it's going to fit that each of those 49 decision tree models to each of these 25 resamples. So it will fit on this part of the data and assess on this part of the data. So fit 49 times, assess 49 times, fit 49 times, assess 49 times. So this might take just a minute. That, you know, we multiply that and that out. It's quite a number of models to fit. So I'm going to pause the video and then come back when it is done. All right, it is done now. So we fit all of these models and we have all these sets of predictions here. And now what we can do is we can choose which one of those we're going to use, and then set that up and see how it did. So for example, we can say collect metrics on that tree result there. So that's all the metrics for all of the, you know, almost 100 models that we tried. If we want to see which ones turned out best, we can say show best here. So it is choosing that with metric ROC, AUC. We could also do it with accuracy if we want. So this is the ROC that we got with these best values here, and it looks like tree depth of 8th was best. We can look at a visualization of how our tuning results turned out, like so. So if let's zoom in a bit here, so we can take a look. So let's notice. So look, tree depth of 1, bad. Stubby trees, no good. And then if we look up here, the tree depth of 8 is best. And then the other ones, you know, are worse, right? Like it kind of goes up and then back down. And it looks like, let's see. So cost complexity. So looks like we get a best value kind of right around here for accuracy. And ROC AUC looks really flat, and we could, you know, like choose something in here. I might choose by accuracy, so I can come in here and get that value there. So if I choose accuracy like this, this is the one that it says is best there. That's that little bump up. You know, and it's a slightly simpler model there. So that seems like a good option. We can also look at the predictions. So we can say collect predictions on that tree res, and it's going to unnest all of those predictions for us, like that. It's quite a lot, so it'll take a minute there. And then we can do something like group by ID, which is that group by each bootstrap. Do ROC. So the true value is shortcut, and then we would say the predicted probability of no, like that. And so that will compute an ROC curve for each bootstrap, and then we can plot that if we would like. So it's going to go through and do all that, and we can see an ROC curve. So, with decision trees, we often get these kind of funny looking ROC curves because it's making like it has 8, it only has 8, the tree depth is 8, so it's making choices in that way. So that is looks about how we expect, pretty good there. And so now we can decide how we will choose our final tree. So we can say select best from the tree res. We can say by metric accuracy like this. So we can say choose tree like that. Choose tree. We could also say select by one standard error on the tree, our tree results. And we could say, if we say minus cost complexity, so what this would do is it says not the best cost complexity, but the and this is on the ROC AUC metric, not the best cost complexity, which is just like the smallest one, but a simpler model. So one where and that's actually the same value. So that's good. So that looks like a good one to choose there. And so what we do is we'll take our workflow, which was a tunable workflow, and then we'll finalize workflow with this tree that we have chosen, and then we can do Lastfit. So Lastfit fits one time on the training data and evaluates one time on the testing data. So we'll give it the split, which has the training and the testing data in it. And so let's call this our final result. So it's fitting, it's one time, and so we can collect metrics on this, and these metrics here are on the testing data, not the training data. And so we can compare this to, say, when we did show best, and we get about the same, roughly the same value. So this tells us if we are or are not overfitting. Decision trees do tend to overfit. So that's something for us to make sure or see that if we have or have not done it. And then if you look in this final result, it has a fitted workflow in here. We have to get it out like this, which is a little bit awkward, but and this is a fitted workflow like this. And we can save that. We can predict on it. So if we predict on the final fitted workflow, for example, if we could, on new data, let's pretend this is new data. Like we could say, we can give it data and we can predict on it. And this is an object here that we can save, say using save RDS or write RDS, and save it and then load it up in another R session and predict on it later for future use. And we can see here, like the first thing here is the first split here is on time, and then we start splitting on tracks, and what else is in here? Time, tracks, time, type, single lap versus the 3 lap. So we've got different ways we can, there's different things that you can do to visualize that. What I would like to do in the last bit of my video here is to show how to do some explainability. So decision trees are nice because they are pretty explainable already. Like you can actually see the decision tree here, how it's going to make a decision. But if you look at time here, maybe we would like to understand how the predictions for whether there was a shortcut or not change with time. And the way to do that is to make a partial dependence plot. And the way I like to do that right now is with the package Doll-X, and Doll Extra has some pretty good support for tidy models. So if we there's a function called explain tidy models, and what we do is we can give it our workflow, our fitted workflow. And then we give it two things. We give it the input data. And so for us, that is the data that it was fit with, where I'm getting confused here. So that's the training data. It actually does not want the Y. So if we say, for example, say Mario train, and let's not give it shortcut like this, and then we give it the shortcut separately as Y. And so let's call this Mario Explainer. So the first step to using Doll-X is to create an explainer. Right, I forgot. Okay, so it does not like it the factor level. It wants it to be an integer, like this. Okay, so we've got our explainer. So here's our lovely explainer here. So it is a workflow. Here's the data that's in here. And now we can use this explainer to do a lot of different kind of things. We can do Shapley values. We can do variable importance. Let's do a partial dependence plot. So the function for this is called model profile. So the first thing we put in here is the explainer, like so. And then we can say, I think that's all. We're just going to use all the variables. Let's use more than 100. I think if we put null, it'll be everything. And then oh, no, wait. That is the variables I want to be explained. So variables, and we're going to say time. Let's put time on the x-axis for our partial dependence plot. Profile. Okay. Variables, and then yes, we can do groups, which is always kind of often kind of interesting. And type. So type for us, remember, is is it 3 lap or one lap here? So do we see these differences? So let's clean that up a little bit, and let's call this partial dependence plot with time, like that. And so it has computed that for us. If you want, you can just use Doll-X's default plotting, but you also can just get out the data that's in there. So PDP time. So there's a couple things. So this is changing the color. This is the aggregated profiles, and this is more like individual ones. So if we do that, we can just we can customize the plot however we want, which is something I like to do. So for example, this label, let's remove from label this workflow underscore business, like that. And then let's make a plot, GG plot. Let's say AES, let's put X on the Y axis. Let's put Y hat. I could maybe do janitor clean names on this to make this easier. And color equals label, like so. Da, da, da. And then let's use geom line. Like that. And I am mistyped the pipe. Like that. And now I can make this plot look however I want. If the defaults are not how I like it to look. So what's on X? That's the time to complete the lap, like the time to complete the record. I'll say some time to complete track because there are different tracks. I'll say Y. That's the predicted probability of shortcut, and say color equals null. And so what is this? This is a partial dependence plot for Mario Kart World Records, like this. Nice. And I can put more info on here. Subtitle, like this is from predictions from a decision tree model. And so decision tree model often have, these kind of funny shapes. Remember that first split was at like 85 seconds, and that's why we see this big drop here. And then we see that we have kind of the same shape for both types after that. But we see this increase up here. That's probably for like some certain tracks, the shapes that we see here. This approach can be used for any kind of model, but we're able to learn about how some probability changes based on what we can get out of these partial dependence plots.
All right, we did it. We tuned and trained our decision tree model so that it's not overfit, but we were able to make use of its sort of low maintenance aspect when it comes to pre-processing. We got pretty good, results predicting whether a Mario Kart world record used a shortcut or not. And then after we, went through the process of training our model, we used the DALX package, which has great support for tidy models, to do some model explainability. Decision tree models are pretty explainable already, but because of the way that they work, often we don't, it can be difficult to just look at the output of a decision tree and say, oh, how does this model behave with respect to, the time in this example, like the length of time it takes to go around for the world record took to go around the track. Making something apart like a partial dependence plot, a partial dependence profile, get you that. So I really like tools like that for being able to understand our models more deeply after we have appropriately tuned and trained them. So I hope this was helpful, and I will see you next time.